Whoa, that just tripled my target. Hey everyone, I'm making a DIY off-grid energy system, and today I'm going to make the generator and explain how it works. So let's jump right in. The type of generator I'm building today, also called an alternator, is used in things like wind turbines, hydroelectric power, and gas and diesel gensets. They work by converting rotational energy into AC electricity through electromagnetic induction. To understand why we make the design choices we do when building one from scratch, I'll briefly go over the fundamental principles that make the whole thing work. I'll do my best to break it down and hit all the important parts in just a couple minutes, so there will be some oversimplifications. The whole thing is made possible by magnets, so let's start there. All magnets emit a magnetic field, and we use field lines to represent it. We can demonstrate the field lines by mapping them with a compass. If we plot successive points with the compass, we can effectively plot the magnetic field lines. If we place a compass by the north pole of a magnet, we can plot a point at the compass's north pole. We can then move the compass so the south pole lines up with that dot, and make another dot at the north pole again. And if we continue to do this, we can effectively plot the field lines. We can also use iron filings to demonstrate the field lines. Two important things to know about the field lines are that they always flow from the north pole to the south pole on the outside of the magnet, and the closer the lines are to each other, the stronger the magnetic field. Also bear in mind that the field is three-dimensional. We can use a magnetic field together with a conductor to create an electrical current, and this is called electromagnetic induction. A conductor is the material that allows the free flow of electrons, and a copper wire wound into a coil is probably the most common type of conductor used in generators. So electromagnetic induction is when a changing magnetic field interacts with a conductor by threading through its enclosed area, inducing a voltage that drives a current through the wire. The copper atoms in the wire have a free electron that we can use the magnetic field to effectively push in the direction that we want. If we push them back and forth, we get alternating current, and if we continually push them in the same direction, we get direct current. Next, to be able to optimize the electromagnetic induction to create more electricity, we need to understand a concept called magnetic flux, which is a measure of the quantity of magnetism passing through a surface. Think of it as the number of magnetic field lines passing through the area enclosed by the copper conductor. So magnetic flux is a combination of the amount of field lines, or magnetic strength, and the size of the area those lines are passing through. The angle also matters. The closer to perpendicular the field lines are to the surface they're passing through, the stronger the magnetic flux will be. So by increasing the magnetic flux, we increase the amount of electricity we can produce. This comes from stronger magnetic fields, larger coil areas, and better angles. We can also multiply the effect by having more turns in the coil. This increases the flux linkage, which is the total magnetic flux interacting with the turns in the coil. So this is what electromagnetic induction all boils down to. As the magnet passes by the coil, the flux increases and decreases, and it's this changing flux that is actually creating the voltage. And the faster the flux changes, the more electricity it can create. And remember, the magnetic field needs to be moving relative to the copper coil to create the voltage and current. If the movement stops, so does the electrical generation. So to recap everything so far, we need to have a strong magnetic field that's constantly moving relative to copper wire coils at an optimized angle. Okay, now that we've covered the basics of how to create a current, we can start to apply that in a practical way in order to build a generator. There are many different types and layouts for generators, but I think in terms of making one in a DIY shop, one of the best options is an axial flux PMG, or permanent magnet generator. Axial flux tells us that the field lines are parallel with the axis of rotation, and PMG tells us that it uses permanent magnets that constantly emit a magnetic field, as opposed to electromagnetic coils that require a power source to generate their electric field, like the kind you'd find in a car alternator. In general, you'll have a rotor and a stator in a generator. The rotor rotates and the stator is stationary. That way you can put the magnets on one and the coils on the other, and as the rotor rotates, it creates the constant motion that we need to induce the voltage. In my case, I'm going to put the magnets on the rotor and the coils on the stator, because it's easier to wire up the coils if they're stationary, but in theory you could do it either way. So now we have a spinning rotor with magnets right next to the stator with coils, but there are a couple things we can do that will vastly increase the efficiency. If we make the rotor out of a steel disc, it'll act as a back iron. A back iron provides a low reluctance path for the magnetic flux to complete the magnetic circuit, which channels and concentrates the magnetic field on the opposite side. Next, only a portion of the lines are making it through the coils, and the wasted lines are called leakage. If we add a second rotor to the other side of the stator and line up the magnets on both rotors and have them pointing in the same direction, the magnets on the second rotor will draw most of the field lines through the coils, almost doubling the flux. Remembering that field lines will always travel from north to south, we can now follow the field path as it leaves the north pole of a magnet on one rotor and travels through the stator to the south pole on the opposing rotor. From here, it again leaves the north pole, and it wants to travel through the path of least resistance, so it travels through the low reluctance of the rotor steel back iron to the adjacent magnet's south poles. From there, it again leaves the north pole and travels back through the stator to the south poles on the opposing magnets on the original rotor. So by combining dual rotors with back irons and matching magnets, we've created a path for the flux that concentrates it and focuses its path exactly where we want it, which is flowing through the stator in a perpendicular direction. So this is great, and we could call it here, but there's one more thing we could do to really boost the flux even more and get more power. If we add some more magnets between the magnets that are already on the rotor, but orient them so the north poles are facing toward the north out-facing magnets, we will increase the flow tangentially along the rotor, which will get us even more flux passing back through the stator. These are called Halbach magnets, and together it's a Halbach array. So the whole magnetic system is designed around minimizing leakage, sending the field exactly where we want it, and boosting the max potential flux. Okay, so that's the layout, and now we can start making the parts. I'll start by making the coils, and that'll set the dimensions for the rotors and the stator. There's a few things to consider when making the coils, and I'll try to show you on this test coil. The induced voltage is tied directly to the number of turns in the coil, as shown in Faraday's law, and you can arrange the turns differently depending on what you're optimizing for in your design. And the radial legs here on the sides should be as long and straight as possible. You can look up Lenz's law or the right-hand rule if you want to find out more about this, but essentially the vast majority of the electricity is produced in these straight radial legs, and almost none of it is produced here in these end coils. So you want to maximize the length of these and minimize the length of these. And next I'll try to get the angles of this taper here just right so that when I lay all the coils out on the rotor, there won't be any gaps along the straight legs, and all the straight legs will be touching all the way around the rotor. So now I'll jump over to the shop and make a coil winder and try to get the coils wound. You don't actually need to make a coil winder, you could just make a jig out of some wood. As long as you can make some really uniform coils, I just thought it'd be fun to make a winder. I'll start by making the actual form that I'll wind the coils around. The wire will wrap around these pieces of round bar, and I'll attach them by drilling some holes in the plate and welding them from the backside. Please remember, likes and subscribes really help the channel grow so we can keep the content coming, and the best way to support us is directly over on Patreon. To make the turning mechanism, I'll mount some bearings in some stands. And weld them onto a base plate. Now I can attach the coil jig to that. And then I'll add a handle to turn it. Then I'll make a quick spool holder for the wire. Okay, here's all the parts, and then one cool thing is that I can make as many jigs as I need for different size and shape coils, and I can just swap these out depending on what coil I want to make. Now I'll just clamp them in place, load up the cover onto the spool holder. The front plate goes on, and tighten this down. I'll carefully demount the coil and add some tape to keep it all in place. Alright, now I have all the coils, I can lay them out and wire them up. There are 9 coils and they get separated into 3 groups of 3 coils. Each group is a phase. I'm going with 3 coils per phase to keep the stator about a foot wide and to balance efficiency, voltage, and to get a smooth sine wave. I'll wire all the coils together in series, except the starting lead in each phase will get wired to its own terminal, and the end lead from all 3 phases gets wired together to a terminal, and that's the neutral terminal. This wiring pattern is called a Y or star configuration, and now we have 3-phase power. Okay, it's all wired up now, so I want to test it before I pour it into a mold and there's no going back. First thing I'll do is check continuity between the phases, and then I'll do a voltage test. So I'll call the black coils phase 1, the white coils phase 2, and the yellow coils phase 3. And I want to make sure that the black are connected, but that there's no accidental connections anywhere else. And then I'll do the same for all of the phases. Okay, so that looks good. Now I'll do a quick voltage test. So I'll set this to voltage. I'll connect between one of the phases. Then I have this I just made up really quickly. It's a couple of magnets taped to either end and a bolt going through. So I can just stick this in a drill. I'll put a piece of cardboard down just to protect the coils. And then when I spin this, I should get a voltage reading. And then I'll test between each phase to make sure I'm getting about the same amount of volts. Everything's looking good, so I'll go ahead and shrink these with the heat gun. Then I'll add some brass bolts to all the terminals. So one end gets a terminal each, and then all 3 at the other end get wired in together. Next I'll make a mold, place the coils in it, and cast the whole thing with polyester casting resin. So I've made a small mold here, and this is just tall enough that it's just taller than all the coils. First thing I'll do is line it with some aluminum foil. Then I'll spray it down with mold release. Put some fiberglass mat down on it, and then I'll add the coils. All right, I want to make sure I get this really well lined up, and then I can also test the height to make sure that no parts of it are sticking out. And now I can mix up the resin. I'll be adding some alumina sandblasting media because that'll increase thermal conductivity of the resin, which will help it avoid overheating while it's running. Next, I want to have a spacer in the center. The axial needs to run through here and it'll help it breathe better. After I finish the pour, I'll let it cure till it's fully solid, and while that's curing, I'll get started on the rotors. First, I'll get the rotor discs cut out. You could do this with a grinder, but I'll just throw it on my CNC. Then I'll get the rotor discs mounted onto the axle, and this needs to be done really carefully so there's no wobble because it'll get really intense at high speeds. I'll use some really thick threaded bar for the axle. I'll mount one of the rotors to a lock nut so it's removable, and I'll weld the other rotor directly to the axle. Then I'll give the rotors a quick test to make sure they're fairly balanced. Okay, the rotors are ready, so now I can get the magnets attached. And to help do that, I have printed these templates, which will help place the magnets perfectly around the rotors. So first thing I'll do is clean off the rotors so I can get everything glued down. Next, I'll get the templates glued down. I'll be using CT1 for this, and for the Americans out there, this is like PL, but even better. So that's the template on, and now I'll start adding the magnets. And ideally, the magnets would be the full width here, but I happen to have a bunch of these already, so I'm going to be placing 2 side by side with a small spacer in between. I don't know how well this will work out, we'll find out, but these size magnets are a lot cheaper than the bigger ones, so we'll find out. And I've got them all oriented. So these are all south facing up, so now I can go around and add all the north facing up. And if I ever lose track, I can make sure that it attracts to this one and repels this one. And it's the alternating north and south poles that creates the alternating current. So now all the magnets are in, I can just double check one more time that they alternate as they go around. And that's looking good. So now I'll mark all the norths. And now I can add the hull box in. I've got all my hull box here, north facing this way. So I just need to make sure that north points in toward the norths. Okay, so all the hull box are in, and the last thing I'll do is put a bead around the edge to really lock everything in. Okay, I'll set this aside to cure and do the next one. The stator's cured, so I'll go ahead and demold it now. The rotors and stator are ready to go, so now I'll jump into the metal shop and build a housing that holds it all together. But before I do that, I thought I'd just show you a couple quick things. Here on the stator, you can see that the coils are really close to the surface, which means I can get the magnets right up close to the coils, and I'll be shooting for about a 1 to 2 millimeter gap between the two, and that proximity is really important to reduce leakage and get the most potential flux going through the coils. And next you'll notice that there are 9 coils, but there are 10 magnet pairs. So this is a 9 to 10 ratio, and it's called a slot pole combination, and it's fairly important. Some ratios work really well, like a 12-10 or a 12-16, but some ratios are actually really bad, like a 12-12 for example. Basically what happens is if the magnets are lining up with the coils in a bad pattern, you can get distortion, and voltages within the coils can effectively cancel each other out. And this can lead to less clean power and lower voltages overall. Okay, let's go get it all put together. I'll use square tubing to make a basic housing. Then I'll run some cross braces down the middle where I can mount the bearings. Now to prep these parts, I'll give the steel on the rotors a quick coat of paint. And I'll file down any high spots on the stator. And now I can start really getting it all together. I can really feel the magnet starting to engage now. As I spin this, this rotor is sort of jumping into position to match the bottom magnets. So I'll get each side of the axle up on one of these bearings, and then bolt the bearings down into the frame. And so here at each corner, I've run a piece of threaded bar through the frame, and then there's just 2 simple brackets and lock nuts here. And so I can put one bracket on each side of the stator, and then by screwing the nuts back and forth, I can adjust exactly where the stator is held, and I can do that for each corner so that I can dial in the stator to line up exactly with the rotors. And each side here on the axle, we'll get a thrust bearing and a lock nut to hold it in place. Now I'll go ahead and get the stator lined up to the fixed rotor. So first I'll adjust the stator to get the gap here with the fixed rotor as small as possible. I'll use a feeler gauge, And I want to get that down to 2 millimeters at the absolute widest and 1 millimeter ideally. Just enough room so that it clears it and rotates freely. And I'll be super careful because as I spin this, it is going to be generating a voltage with these exposed terminals. Now I can just rotate the free rotor and it'll tighten in. As they get close, the pull between the two rotors is getting really strong. Then I've got a lock nut I can tighten down to lock this in place. Okay, that looks good. It's really close to testing. I just need a pulley wheel here on the end of the axle to drive it. And I'll just make a quick pulley wheel. I'll thread on 2 nuts and I'll tighten them down really tight against each other. Now I'll just use a grinder to turn this down and add a groove in the center. And I'll make a makeshift pulley for my drill just for testing. Okay, for this initial test, I've just got it clamped down to the table. I've got a voltmeter hooked up to it, and I've got a tachometer here so I can tell how fast it's spinning and what voltage I'm getting at that speed. So I'll just throw the belt on it and get it going. Okay, I got about 5 volts when it was spinning at around 500 RPM. So I'm pretty close to my target. I think it scales linearly, so it'll be going 7 times as fast, so I can multiply the voltage by that, which means I'd be hitting about 35 volts. Ideally, I can push it up to about 40 volts, but we'll see what I can get with some tweaking. And I don't want to spin it faster than 500 without getting an enclosure on this, so I'm gonna go ahead and throw some sides on this. I'll use wood for the housing so it doesn't interfere magnetically. After really trying to dial in the last design, I just couldn't squeeze enough power out of it for what I wanted to do, so I've rebuilt the rotors and the stator with an updated design. I've gone with 16 poles on the rotors instead of 10, so that should help a lot, and then I've increased the coils from 9 to 12, so now I'm at a 12 to 16 ratio. I really spent a lot of time trying to get the shape of the coils just right and get the radial legs nice and straight, so I should be able to get a little bit more power out of that. I've increased the turns a little bit, and overall it's about 1.5 times more turns than the original design, and it's a little bit thinner too now, so I can get the rotors closer together and hopefully boost the flux that way. So I'll get these thrown in the housing and see how much power I can produce. So while I'm putting it together, I just wanted to show you something to demonstrate how important the proximity is. I've got one of the rotors dialed in really close to the stator here, but there's still a big gap on this side, and I'll just give it a spin. So pretty slow spin, and it peaked at about 5.5 volts there. So now I'll go ahead and close this gap and we'll see the difference in the voltage. Okay, I've got it a lot closer, but the whole system isn't even dialed in yet, and I'll just give it another spin and up to 11 volts. So it's a huge difference just in closing that gap. So now I'll just finish dialing this in and see how much we can get. Okay, here we go for the first real test of this version. I've got a tachometer on it again, and this is whole volts, no decimals. So let's see what we get. Okay, we just hit 40 volts at 600 RPM, so this thing is putting out way more volts than the last design. I don't want to run it faster than 600 without an enclosure on it, so let me throw that on it and I'll try to get it up a little bit faster. This is great. I overshot my goal voltage by about 3 times. The original goal was 50 volts when the generator is spinning at 3000 RPM, and I just hit 52 volts when it's spinning at only 1000 RPM. So when I triple the speed of this, the voltage would triple too to over 150 volts. This is actually too many volts for my application, and I'll probably need to dial it back a little bit to avoid voltage spikes that could damage my charging equipment. So anyway, I'm super stoked on the results, and this video has taken a really long time to make, so I'm just gonna call it here for now. And if you wanna know more about the build, I'll try to put together a packet of information, and when it's ready, I'll link it down below. But I'll be back soon with the next video where I'm gonna rectify the alternating current into direct current. I'll hook this up to an engine, and I'll charge an off-grid battery system. So keep an eye out for that one. I'll try to get it out as soon as I can. Hope you enjoyed this one. Thanks for watching, and see you again soon.